Hey guys, and welcome to the fifth section of this video course, Performance and Maintenance. In the first video of this section, creating index and viewing plans of queries, we will look at querying our data, explaining the query plan in order to analyze the performance of data, and then finally optimizing our data by creating indexes. Let's begin by creating an index. We need a simple load for the same. So let's get our server up and running. Now, I will import the data that we need to operate on into the database. We will execute the Mongo import command from the shell, which will import the needed file into the current directory. Let's begin the Mongo shell by executing the Mongo command in the command prompt. In the shell, we will execute the count command. Our task is to write a query to find all the zip codes in a given state. So our first step to do this is to analyze the plan. We will execute this query for the same. Okay, so take note that the value of the stage field in the result is call scan. Now this means that all the documents of the entire collection have been scanned one after the other in order to find the matching documents in the entire collection. Let's look at some of the other results which are returned. The end return value is 6446. Now this is the number of results that matched the query. The total docs examined and docs examined field have values of 39732, which is the total number of documents scanned to retrieve the required results. This also indicates the total number of documents which are actually present in the collection. The execution time millis is the time in milliseconds which is required to retrieve the result. Now that we have analyzed the plan of the query, we will work on improving the performance of our query. So we are going to be targeting three major areas. The first is execution time, then using compound indexes, and then finally using covered indexes. Let's start with the first option, and that is improving execution time. So the one thing that you must have noticed in the previous result is that the query doesn't do too well in terms of performance, and we can actually step in to improve its execution time, thereby affecting its performance in a good way. Now, a simple limit applied to the query will affect the query plan to a great extent. Okay, so let's find the query plan again without the index, but with the limit clause like this. So we will execute the same query, but limit the results to 100 only. Now note the resulting query plan this time around. Notice that we haven't created an index, but still we can see an improvement in the query execution time and the number of objects scanned to retrieve the results. The explanation for this is simple. Mongo ignores the scanning of the remaining documents on reaching the number of documents specified in the limit function. All in all, we can conclude that limiting the number of documents only when you are sure of the maximum documents to be accessed will give you a better execution time and may also lead to a better query performance. However, in the absence of an index, if the number of matches is not met, the collection can still be completely scanned in its entirety. Okay, so let's move on to the second category, improving performance using compound indexes. Let's play around with compound indexes on the state and the pin code field. The order of the index is ascending in our example, and it's not really of importance unless you plan to execute a multi-key sorting. This helps to decide whether the result can be sorted using only an index or whether Mongo needs to sort it in memory later on, before the required results are returned. We will create an index on the state and pin code fields by typing this command. We will now execute our find and explain query. The result shows us that there is a significant improvement in the plan of the query. We can see that the input stage field now has the IX scan value, which shows that the index is actually in use now. Finally, we come to improvement of query performance using covered indexes. So for this, we will understand the meaning of the value of the execution stages, that is fetch. To get a clear view of the same, I will first explain in short how indexes actually operate. So basically, indexes will store a subset of fields of the original document in the collection. The fields present in the index are kept sorted in an order which has to be specified during the index creation. The indexes also have an additional value which acts as a pointer to the original document in the collection. The pointer is stored with the index entries matching the query and is then used to make other input and output operations to fetch the complete document from the collection. This is then finally returned to the user. The index is referred whenever the user executes a query to get a set of matches if the query contains fields that an index is present on. Since we only want the pin codes, we will modify the query and view its plan. Let's look at the value of total docs examined and the execution stage, that is projection fields. The data that we requested in the projection can be obtained from the index alone. We have scanned a total of 6,446 entries in the index as depicted from the total keys examined value. Our query did not fetch any documents from the collection, since the entire collection was fetched from the index. So you can see that the value of the total docs examined is 0. Also, since this collection is small, there is no significant difference in the execution time of the query. This will be more evident on larger collections. As compared to category 2, the results indicate that making use of covered indexes gives us a better performance than making use of compound indexes. This wraps up the first video of section 5, where we learned about analyzing a query plan and ways to improve its performance.